But I want you to go through the homework problem, so figure out what's going on in there. It's tedious detail. Yeah. But the physical concept, like what in each step, how are we calculating? That's more important. I want you to understand why you want to do the calculation and what's going on. Okay. But the mathematics, the detail is in integration over this, integration over that. That's actually not that important. Okay. So next, I want to talk about changing state theory. But before we talk about changing state theory, we need to have a better understanding of a very important concept in chemical, in chemistry. That's potential energy surface. The idea of a potential energy surface happens in all sorts of chemical problems. So in chemistry, we are very accustomed, we think about potential surface every day, basically. So whenever you have a chemical reaction, you will plot, oh, okay, I have a chemical reaction, so I will have some reaction energy of the system, right? And then we have some reaction coordinate. And along this reaction coordinate, we have some reactant and some product. Let's say we have a reaction A plus B, C plus D. And we will not to confuse. A plus B became P. So here you have A plus B, you have a P. But what exactly is a reaction coordinate? And what exactly is this energy talk about here? This could be actually a little bit tricky. Mathematically, or very fundamental in physical chemistry, everything here, to have a potential energy surface, we need to start with von Oppenheimer. Approximation. You learn this in quantum chemistry, right? So what is von Oppenheimer approximation?
The motion of nuclear is relatively slow compared to electrons.
Yes, but you are talking about the reason or the origin of a von Oppenheimer approximation. Why we can make a von Oppenheimer approximation? But what is von Oppenheimer approximation?
通通位方程等于 nuclear 位方程和 electron 的位方程。
Yeah, so the separation of electronic and nuclei variables. Okay, so in von Oppenheimer approximation, the wave function of a molecular system can be written as an electronic wave function product some nuclear wave function. And if you assume this form, your Hamiltonian can be written as a kinetic energy of the nuclear plus electronic Hamiltonian. And your electronic Hamiltonian solve the electron in ground state for eigenstate for a stationary state of the system. Then you solve electronic part of the reaction of the problem. And then electronic Hamiltonian. Those electronic wave functions are eigenfunction of your electronic Hamiltonian. So you have an electronic, and those are functions of nuclear coordinates So we define this is electronic energy at nuclear coordinate. Given a set of nuclear coordinates, I solve the electronic problem. I get the electronic energy. This electronic energy defines the energy of the system, nuclear plus electrons at this nuclear coordinate. Okay? So, for each nuclear coordinate, you have electron energy. This defines the potential energy surface. And this R here includes only the relative positions of your N atom system. So if your molecule contains N atoms, in total there are 3 N degrees of freedom, but you have 3 translation, 3 rotation, assuming nonlinear molecules. So there are 3 N minus 6 coordinates in this. And we normally call this vibrations, right? Relative. Okay, but in a molecular system, you can have a very large. In chemical reactions, you can have a very large amplitude rearrangements of atoms. So those are not simple vibrations. You can have a more degrees of freedom that's more than vibration. So this is what the potential surface we're talking about, actually. Okay. Now, for simplicity, we can consider a reduced 2D system. That is, we consider A, B, C in a line. Okay, so we restrain those 3 atoms on the line, but then we have 2 coordinate RAB and RAC. I'm not very good at drawing 3-dimensional things, but I'm going to try here. The idea here is, in this case, we have 2 nuclear coordinates. So your energy is a function of RAB and RBC. Here. Yeah. So let's say you have your energy, and this is RAB, this is RBC. Okay, let me try. So let's say you have, and let's plot this. Okay, what I'm trying to draw here is your cut section here, another cut section here. This is a valley, another valley here. Okay, those are contour lines. Contour lines is we draw a line on the same energy. Okay. So from here is actually your when your system is at reasonable A, B, C, but so this is A plus B, C. Here is A, B plus C. Okay, because here this direction is RAB, so here is small RBC but large extended RAB, so AB is large. Here is large RBC but small RAB. Okay, yeah. I don't know. Can Okay, thank you. So, here from the reaction, if you have a reaction A plus B, C became A, B plus C here. Basically, we start from here, want to go here. And how do you go from here to here? In reality, a system has kinetic energy. Okay? So in reality, now assume that actually here is a valley, this is a valley, here is some minimum energy point. This is another minimum energy point. You want to go here to here, you need to climb this ridge and then go down this ridge here. So go up and then go down. You follow a path like this. In reality, you do not actually go through the path that at each point you have a minimum energy perpendicular to this path. In reality, you don't do that because in reality you have a kinetic energy. You actually fly on top of this surface. Okay, and you can go. You have some freedom to go different places and then go to this point. But let's assume you want to spend the minimum amount of energy to go from this point to this point. What are you going to do? Well, you always go on in this part. You always go on a climbing direction. You always go on the direction of the gradient. Are you following me? Okay? And direction of gradient means you have the direction that have the maximum change in potential, in energy, but along other direction, you always follow in a minimum. Okay. So this path from this point to this point, I draw here, could be a minimum energy path. And if you follow the minimum energy path, the minimum energy path is you have an energy gradient along one direction, but in all other directions you stay in the minimum. So in this case, if you draw potential perpendicular to this path, this potential is always in the minimum. You always follow the minimum point. This is definition of minimum energy path. So this minimum energy path in this case we have two-dimensional space. It could already be a complicated path. It can be non-smooth or even wiggly, going from one point to the another point. But if we define this path as our reaction coordinate. So normally we define reaction coordinate using minimum energy path or something similar to this. Minimum energy, maximum gradient. And then draw energy as a function of the extent of a reaction on the reaction path, on the reaction coordinate. You get this reaction profile. So this is called reaction profile. PROFILE. It's a one-dimensional potential energy surface along the reaction coordinate, defined as minimum energy path. And along this minimum energy path, you definitely will pass through a point. In this point, it's a maximum in this minimum energy path. Okay. This is called a saddle point. So this is the saddle point here. And what do we call this saddle point? Transition state or activated complex. Transition
Is minimal energy path always the 1D reaction profile?
We basically we normally define 1D energy profile using minimum energy path.
Is there a proof that going the path where its perpendicular gradient is 0 is going to be the minimum energy?
Well, actually, minimum energy path corresponds to so-called least action path.
Is it?
It's the path that you will go through if you do it very, very slowly, okay, at the 0 temperature.
So the minimal energy is taken by step. It's
Step by
not.
step.
So there is any other? Is there another? It is possible for another path to exist such that the overall energy might be lower.
There's no such thing as overall energy. Yeah, overall energy here makes no sense. You can define action. Action in classical mechanics. You can define action. And this basically is a least action path. Okay. And it's the Newtonian dynamics path at the 0 temperature. If you have no kinetic energy. In reality, there are many more dimensions. And there are many, many more possible paths. So from one point to another point, there could exist multiple minimum energy paths. The minimum energy path could travel through not a simple saddle point. Actually, simple saddle point means you have a one direction as maximum, but in all other directions you have a minimum. Okay. But in reality, you can have other type of saddle points. You can have a second order saddle point, including you have two directions are maximum, all other directions in minimum, etc. But in this case, we assume simple saddle point, okay, and a well-defined reaction, one-dimensional reaction profile. It's okay. So in reality, things could be more complicated. And here we assume we have a simple saddle point such that your partial energy, partial R and N along the reaction coordinate at the transition state, this will be 0. and the second derivative I change state will be smaller than 0. And for all other coordinates, this will be this is actually not necessary. Not necessary. All paths, everything, everywhere, will be first derivative will be 0. Yeah. But second derivative, as changing state along relation coordinate will be negative. But then r not equals to relation coordinate, at changing state will be greater than 0 square. So this is how we define simple settlement point or simple relation profile. If we make this assumption that the system, the relation we are interested in, is in this sense, and Born-Oppenheimer approximation applies, we can define a relation coordinate. We can define the changing state as a simple saddle point with those conditions. Now, at the changing state, we can draw a dividing plane, saying that on the left of the dividing plane, those are reactants. And once the reactant passes the dividing plane, it goes into products. And at the transition state, this transition state or activated complex, here I will call it C double dagger. Normally in chemistry, you use a double dagger to indicate that this is something unstable. Okay? So this C is actually imaginary. It does not actually exist. It's not true. A changing state, you cannot observe a changing state. Okay. So I performed an experiment. I saw something that must be intermediate, must be minimum, not maximum.
Partial E, partial R, more than 0 for R doesn't equal RC. Isn't that true for the entire reaction profile? Because we're going along
at changing state. At changing state. This is only meaningful at transition state, not the whole reaction profile.
But when we're going
I'm talking about the property of this point.
Uh-huh.
So I consider only property of this point, saddle point.
But is that not true for the other points too?
No.
Because I'm imagining like going through a valley and going up. So left and right will also be, because it's going to be like this, right? So it's going to be more than 0.
At this point it could be negative, but at this point it will be positive along reaction profile. So at this point, second derivative along the reaction profile is positive.
Yeah.
Here is negative.
Yeah, but that's for R equals RC, right?
Yeah.
And there we're writing R does not equal RC, so it's like the size, right?
No, because in other coordinates you can do something else. So this is A plus B to P.
Uh-huh.
You have another path that going A plus B became PQ. Another product. Okay? This is a multi-dimensional space. This is a multi-dimensional space. Actually, this concept of stability, this is actually a stability test. This is a stable minimum. Okay. This property only exists at near equilibrium point. When you go away from the equilibrium point, there is no guarantee that your second point, this second derivative will be positive. It could easily be negative. Yeah.
But we're choosing this specific path because
Mm-hmm.
it's more negative, I guess. It's goes to a more stable point then.
No, definition here, I call this minimum energy path.
Yeah.
So along this path, only for other coordinates, the second derivative will always be positive.
Yeah. So.
Along this path,
Yeah.
not everywhere.
Yeah.
Only when you sit along this path.
Yeah.
Yes.
So what I'm asking is, why is there an extra transition state explicit term? Because that should apply for the entire path, right?
No, all others if I write here at this path, is this going to be better for you?
I'm asking if it's true or not. Like, I don't know if it's
This
true
is
or not.
true.
Oh, okay.
Okay, but I don't care because here I'm trying to define the property of a changing state.
Okay.
So I constrain my second derivative, partial derivative at changing state
Okay.
position. Okay? Yeah, where am I? Oh, here. Now, to derive the changing state theory, we only need one extra thing. One thing more. That is, now, so we assume Born-Oppenheimer approximation. We assume a simple relation coordinate can be found. We assume the change state is a simple saddle point. Okay? And then we assume the critical assumption here is we assume return and the transition state reach equilibrium. So this is not a true equilibrium in thermodynamic sense because you can never measure the concentration of the changing state. So we call it quasi-equilibrium. Over A plus B So this is the most critical approximation in simple changing state theory. We assume the return and the changing state can reach a quasi-equilibrium. Okay? So with this assumption, the C then decayed, then became product. And we assume that this rate for C to become product is some K double dagger. We put double dagger on it because it's actually not real, something real. It's not something real. And you can actually say K double dagger is like lifetime of changing state. And in principle, C can decay into either product or return. You can go back to return, but we assume we always go to product. So 100% into product. No back reaction. No back reaction. No back reaction. No backward reaction. No reverse reaction. So when change state decays, you always go to the product. So we make an approximation of a quasi-equilibrium. We make an approximation of a changing state. When you reach a changing state, you always go to product. Then we can write down the definition of a rate law. We can write one thing. Rate law of this reaction is, here I use V, this is using Bob-Selby's notation, is your rate constant times concentration of A and concentration of B. Rate law. Okay. But then this rate is determined by how you see your changing state decays into product. So this rate actually is this K double dagger times the concentration of the transition state. You can consider this is the rate determined state. So combine these two, we can calculate rate constant. So your rate constant by molecular rate constant is, they must be equal, right? So K A B equals to K double dagger C double dagger. So the rate constant will be K double dagger times AB this. And you see, this is something like an equilibrium constant, right? So let's try to calculate this. Well, here we need to do conversion between equilibrium constant in partial pressure and the equilibrium constant in concentration, Kp and Kc. We need to do a little bit. So thermodynamic equilibrium constant will be C double dagger divided by some standard state concentration A dot divided by C0 times E divided by C0. Okay. So it will be C0 times A B C. And then A concentration will be PA divided by RT, because A concentration is N divided by V. Using PV equals to nRT, remember this relationship. Okay. So replace everything here. We have a relationship between Kp and Kc. So Kc equals to C0 RT P0 Kp. So your rate will be K double dagger times this. Okay. So this is Kc divided by C0. Kc divided by C0 will be RT over P0 times Kp. So this will be K double dagger times P0 RT Kp. Now we learn how to calculate Kp already. The thing we calculated last time, the equilibrium constant is equilibrium constant in pressure, because the reference state are gas phase states. Okay. The key thing here is we need to figure out K double dagger. And this is the tricky part. This is the tricky part. There are a few ways to do this. I'm going to do a simple version following Bob-Sylvie's argument first. Okay. Then I'll come back and tell you my point of view on this factor. So Bob-Sylvie here says that, well, let's first look at the unit of the thing. And if you do it carefully, you see that unit of this is frequency, in frequency. And it's easy to see here because this is a single molecule reaction. Concentration here, concentration divided by time is the rate. So this rate constant mass in inverse time unit. Okay? So it will be a frequency that has to do with the motion of the changing state. So let's say you have some changing state here doing some, let's say, vibrational motion. Okay? And this K double dagger should correspond to the frequency of this vibration, because when you vibrate once, it goes to the product. Okay? So it depends on how fast the motion on top of this this mountain is. If you run very fast, you do a very fast vibrational motion on the top of mountain, you fall off quickly. If you do a slow vibration, you fall slowly. Okay? So let's assign motion, vibrational motion of this molecule across the reaction coordinate on top of the reaction coordinate, some frequency nu. And then we set this, so this frequency is nu. And then we say, okay, then this basically is defined by nu. So your rate now will be nu times P0 RT dP. Okay? Now let's calculate this part. And this part has to do with this partition function of a different species. Okay? Internal partition function of different species. Well, we need to define a few things first. Let's assume this energy from here, oh no, not from here to here, so actually here to here. Now let's assume. So we need to compare A, B, and here is C double dagger. Here, change state here. Let's assume this energy is delta epsilon 0 double dagger. This energy is delta epsilon 0 double dagger. Activation energy. Defined as as I already said, this is the electronic energy of a system. Defined as the difference in electronic energy of a C double dagger and A plus B. Okay? So I'm going to write down this Kp. This is from last week's lecture. It's basically E plus 1 times Q C double dagger divided by Q A for each Q, single molecule partition function for the ith chemical species will be, well, kinetic part h squared 2 pi m k p 3 half. This is 1 over lambda to the cube. Translational part. Rotation part, symmetry number times rotational rotation. This is power of 1, so here we actually assume linear. If it's nonlinear, you have a sigma A, sigma B, sigma C, then T to the cube, then square root everything. Okay? And then vibration. Multiply all vibrational modes alpha, exponential L beta h bar omega alpha exponential L minus L beta h bar omega alpha. What? Vibration. And then electronic. Assuming the electronic ground state, so you have minus beta electronic energy. Now, what I want to do here is, this electronic part here is simple because each one have this exponential factor, right? So underneath here you have electron energy of A, electron energy of B. Here you have electronic energy of C double dagger. So basically, overall you will have exponential beta electronic energy of C double dagger minus electronic energy of A and plus minus electronic energy of B. So you have activation energy here. So I'm going to erase this and write here exponential minus beta epsilon 0. this is the activation energy. So activation energy in this case is the total difference in the electronic energy. Compare your change state and your reactance. So maybe this makes it a little bit simple. Now, this vibrational part has an interesting property. That is, at the reactant minimum, so for A and B, their vibrations corresponds to this. Okay. But this vibration, the total number of vibration modes, reduced by 1 in the changing state. Because 1 vibrational mode in A plus B, this reaction coordinate, this vibrational mode, when it goes to the change state, the frequency is negative. It's replaced by this mode we talk about. Okay? So actually, your C double decker, 1 vibrational mode should be considered separated. So we consider this as Q prime C double decker. This is all positive frequency. So Q prime here includes only positive frequency modes. However, in the change state, it's a settle point. There's an imaginary frequency mode. There's a mode that's spatial along the reaction coordinate. It's a spatial mode. So we separate this mode, and I call it QRC. This is the mode along reaction coordinate. And what is this mode? This is this mode. So here, you cannot define frequency over this motion. Here it's okay. Here there's a vibration frequency here. But when you climb up, go to here, it's no frequency. So number of vibration modes in the change state actually is reduced by 1 because along the reaction coordinate, there's no vibration. There's imaginary frequency. And we separate this one. Although we separate this one, we still treat this as if it's a vibration. Okay? Yeah, it's weird, but this is how it's done in observers. Look. Okay? So, what's going on here is we consider QRC as and we use that frequency nu here. So H bar omega nu for this mode will be He. Okay. So what's going on here will be, but then we further assume this frequency is very small. So we further assume H nu is much smaller than KBT, smaller than thermal temperature. This is an assumption that put in an energy scale for this mode, for this mode. So then this, if this is true, this is a very small number, we can expand the exponential, right? So here you have 1 minus half beta h nu. Here you have minus half beta h nu, right? 1 minus beta h nu. Let me do this now. 1 plus half beta h nu minus 1 minus half beta h nu. So you have h nu. Okay? Beta h nu. 1 over beta h nu. And 1 over beta h nu is kBt divided by h nu. Then you have a nu here. Here you have this Kp prime, that is, you use this, but Q prime C double dagger times QRC. So let me do it slowly here. So now our K will be RT 0 AP this part and then mu QRC. I intentionally put nu and QRC together. KB prime. Thank you. And this nu as QRC, we can actually independent of nu. And this is good because we have totally no idea what nu is, or how to write down nu. And if you go back to check the idea here, this actually corresponds to the concentration change, right? So again, this factor actually defines the left hand of C double D. So this KVT over H actually is a factor defining the left hand of C double D, the changing state left hand. in this case, we use a very kind of, I don't really like this derivation here. And you can find a more extensive or more tedious derivation, assuming the change state is defined as like a small range. Consider the velocity passing through that range, that range of a change state and blah blah blah. In Levin's physical chemistry textbook, I uploaded Levin's physical chemistry textbook, chapter 22, I think, to NTU Cool. So in NTU Cool, on NTU Cool, you find a chapter on this. It's from Levin's physical chemistry textbook. I don't like it either. I think it's not better. It's not better. To actually derive this is a very tricky thing. The best argument for this is this. I don't know. Another argument for why P over H. Another argument about why this is the lifetime is this. It's a lifetime. The change state in principle is unstable state. Okay. So I'm going to argue this from uncertainty principle. Uncertainty principle says that delta S and delta P right? But there's another form of uncertainty principle. This is in terms of uncertainty in position and the momentum. You can write the uncertainty principle in terms of uncertainty in energy and lifetime. So uncertainty principle exactly can be translated into delta E times delta T. For any metastable state, a fundamental quantum mechanical principle called uncertainty principle dictates the lifetime of the uncertain state. It's energy uncertainty times the lifetime. Here, this delta T should be interpreted as the lifetime. So this is uncertainty principle. And uncertainty in classical phase space as I should say unit we don't have time to derive this, but I talked about this already. In classical statistical mechanics, when you want to count the number of states in a phase space, there's a unit value of H. Okay, because there's uncertainty in position and the momentum. So within this volume, there are infinite states in this volume, infinite classical state in this volume, but they all count as one quantum state. Fundamentally, this is uncertainty principle, kind of a result of uncertainty principle, consequence of uncertainty principle. So, if we have a system, a metastable system, like the change state, at a certain temperature, we know the system, the state will have a thermal energy that can be attributed to its uncertainty energy. So this will be the energy scale of a thermal fluctuation, kBT. So kBT, so we will have E times your lifetime, still is delta T, should be approximately H. From here, you will say, okay, this is H bar is H over 2 pi, right? And certainly it's something smaller than H, right? But also in quantum mechanics, you know that only very few scenario you can have a state that exactly matches this. In most cases, it's greater than this. And now I'm going to adapt this value, H, here. And this tells us, well, the lifetime is defined by H over kVt. So lifetime is this, then decay rate. kVt over H. So the idea here is, the state here is not stable. And how unstable it is depends on temperature. Actually, temperature defines the energy fluctuation of this state. Okay. And energy fluctuation and the lifetime can be connected by uncertainty principle. Okay, so from this, we can calculate the lifetime. So this picture tells us that the decay of the transition state is driven by thermal fluctuation. Thermal energy pushes this transition state around. Okay? And let the transition state into the product. So the decay of the transition state is due to thermal fluctuation. And its lifetime is defined by the energy scale defined by thermal fluctuation through uncertainty principle. So now we have this heavy T over H vector. I like this argument better. Okay. So basically combine everything. I'm not going to repeat it anymore. Combine everything. You have your K rate constant will be kVt divided by H. Now I'm moving this lifetime in front and V0 RT. Sorry about this stupid factors. V0 minus kVt minus 1. Q prime, this prime is removing the QRC. Okay. So there's only 3n minus 7 vibrational modes in this. Divided by 3. C double take QA, QB minus Boltzmann factor, exponential minus epsilon 0. Activation energy. simple way is to write this as this as K double theta. Basically, the equilibrium constant of your reactant and your changing state. I'm not going to evaluate this today. We are going to do an example to evaluate this for a simple reaction next week. But through our practice next week and in your homework that's going to turn in today, you should be able to calculate this. All right. So let me remind you, when we derive change state theory, this is the end of the change state theory. We make a few approximations. We assume Born-Oppenheimer approximation, so we have a potential energy surface. We further assume that in this potential energy surface, a simple reaction coordinate can be defined, and a change state with a character of a simple saddle point can be found. Okay? We assume quasi-equilibrium between reactants and changing state. We assume there's no recrossing. The changing state can only decay into the product. If that's not the case, actually, in principle, if you assume this vibration, it can go to the product or the reactant. So the rate should be just half of this. Okay? Yeah, but we assume it always go to the product. And we assume classical nuclear motion, no quantum tunnel. That's because you always have to go go to the change state. If tunneling can happen, you don't need to go to change state. And we assume that the reaction coordinate can be separated from the other degrees of freedom, the other coordinates. Sometimes that's not possible. Okay. So we made many approximations to reach this result. But this is a result that we know how to calculate. So this defines a microscopic rate constant for a system. And this rate constant, obviously from those approximations we made, is the upper bound. Is an upper bound. So when you, in physics, when you know something is an upper bound or a lower bound, you can then do variational treatment to improve the result. The idea here is, well, actually, one can construct a variational changing state theory. So we're talking about changing state theory. And there is a variational version of this. And the idea is, we still assume there's a simple potential energy surface. But instead of define the top of the as a changing state, so this is the conventional simple changing state theory. We can actually say, well, let's assume this real changing state, the real system, the real geometry of the molecule that actually how to say that represent the changing state. It's not something here, actually it's something here. So instead of using this as a changing state, you choose another point. Another point. So when you change this point as your changing state, I call it changing state prime, you can then go through everything. Basically, this is the same, this is the same. You recalculate the partition function here, right? So you calculate another rate. You can change this. You can even move this line here. Whatever, you change this. You change this. So you change to find, because that's an upper bound. Okay. So we try to find minimum case, minimum rate. And that will be variational change rate. And this rate will have a beta agreement with experiment. You can see that when you go this direction, we'll go to this direction, this activation energy will decrease. So the rate of this part will increase. Okay? But then the partition function will change. The partition function will change. Sometimes the partition function will change such that this part will decrease the rate. It's very constant. Okay. So then you find a beta change state. Okay, change state prime. That's beta. But if you change it, then this part will not decrease. Then the change state, the best you can do is the change state on the top that minimize this term. So that variational change state theory actually is a balance between this part, this molecular structure, and this part. And I'm not going to go into any detail, and of course this kind of variational change state theory calculation cannot be very easily performed. So we're not going to go there. Okay, but I want you to know that there is something like this. Okay, any questions? What?
I didn't get this part. So we're setting a lower point as the transition state point. Is that what it is?
You can choose any place as your change state. And using change state theory to calculate a rate constant. But because our approximation dictates that this calculation gives you an upper bound. Okay? Any way you can reduce this value, that gives you a beta physical result. It's a variational process. Think about it.
So we use the same potential energy surface.
Yeah.
And but just to change the position.
You change when you go here. You have a different molecule. You have the change state structure is different from this one. Yeah. And sometimes when you change the structure, the vibrational modes, everything changes. And that reduce this part of the partition function. So you get a rate constant that's smaller. What? Variational. Because this is an upper bound. When you have an upper bound or lower bound, you can do variation. That is actually in some reactions. The rate determinant step that govern that detects that defines change state is not on the top. It's somewhere here.
So suppose we scan the entire from the saddle point all the way to the bottom.
Yes.
And I guess we find a K that matches the experimental result?
Not really matches, but you can find a K that's minimum. And that's the best case predicted by this theory. Because this theory yields an upper bound. Okay.
But like, what's the like physical explanation behind choosing another transition state?
Because that structure here, that structure is more difficult to get to. You are only looking at this exponential electronic activation energy difference, this Boltzmann factor. But the real equilibrium constant here is determined not just by this factor, not just by this energy. It's also determined by the partition function of the molecular structure. Okay? So for example, if that molecule generates, and that state generates a very high strength interaction, so that increase the should we increase or decrease? That changes the vibrational frequency. That changes the vibrational frequency. Okay? And that will change the vibrational partition function for you. So you will change the partition function. And that, so basically what's going on here is, this is the electronic state, electronic energy part. That somehow is obvious. In this case, it's obvious. It's the obvious factor that tells you some, oh, this energy detects this Boltzmann factor, the probability. But there's more. There's rotation and vibration. Diffusion frequency here. So this part actually is the factor in the equilibrium constant that tells you, is the vibrational mode, vibration, difficult to reach or not. So sometimes, well, this electron energy, this is the electron energy part. So you go to your intuition will be, you go to here, it will be easier to get here. The activation energy is smaller, right? So, well, you should have a higher rate. How come it will be slower? Yeah. Because when you decrease the activation energy, the rate should be higher. But that's just part of the story. Because there are vibrations here. Your transition state could have a very different vibrational structure. That makes its vibrational part, vibrational partition function, vibrational part very difficult to reach. It could even generate a vibrational mode that's higher in energy, so you have a higher 0 point energy. When you add up the 0 point energy, it's actually high.
So in this case, we're calculating from initial state to transition state directly. So it's not like
actually you can even go here.
No,
the
yeah.
dividing plane is not necessarily just on this half. It could be also on this half.
No, because I'm thinking like if you're going from the initial to the transition state, aren't you going through each little step?
No.
You're going directly, right?
No,
You're
this is
directly.
a misunderstanding.
Uh-huh.
We are doing statistics, so in this case,
Yeah.
we don't care how the system reaches transition state.
Okay.
We only calculate the ratio of the molecule in the transition state versus number of molecules in the reactant state. We only calculate the ratio. We don't care about how it reaches transition state. There's no path in this treatment of a transition state theory. Okay, so that's why it's different from the collision theory. It's tricky. So the last part, in the development of a transition state theory, actually the key paper of the transition state theory is from a paper by I think it's Irene, Evans, and Polanyi. Okay, in 1935. The early development of train state theory actually it begins even before quantum mechanics in the early 90s. And the full development of it, combined with experimental verification, is actually in the 60s and the 70s. So it takes like 50 years for the whole idea to be completed. So there are some tiny little details I cannot cover fully in a 3-hour lecture. But I want you to have in mind the basic idea. So the approximations I went through, and this formula here is actually very simple. This is an equilibrium constant, and this is a lifetime as long as you understand where it comes from. Okay, and this is just a changeable unit. That's it. So simple. But before everything here is kind of being sorted out, Irene came up with a simple sort of quasi-empirical. So I really want to connect this to experiment. So he writes the transition state by considering somewhat dynamic. So thermodynamic K double dagger is basically concentration. So if we define this, focus on this, K can be simply written as KT divided by H. And the idea is you have A plus B in equilibrium with C. Double dagger, and this is K1, this is K-1, and C double dagger became product. And you assume this is in equilibrium, so you K1 divided by K minus 1 is this is some equilibrium constant. Okay. So would be in this kinetic definition, we don't need this. We'll define this as K double dagger. And this one, your apparent rate constant, so you have this. Your rate constant. Another way to consider this is we still have a thermodynamic C naught. but we consider the standard concentration is 1. So it's a unit transformation. You need to change the unit. You need to consider this. Finally, we will define rate constant. Now, in this case, will be your K double D. That's your K. So your rate constant will be, and we figure out that this K double D is this inverse lifetime is KBT divided by H. So Irene first derived the equation like this, basically using kinetic argument. I say this is quasi-empirical because this part is empirical. There's no microscopic partition function whatsoever in this equation. Okay. But then we know that thermodynamic delta G is minus RT nature of K. So we know that thermodynamic equilibrium constant is connected to free energy. And this will be a free energy of activation. Okay, it's the difference between changing state and the reactant. Okay? And this will be delta H double dagger minus T delta S double dagger. So in reaction, delta G is delta H minus T delta S. So double dagger means we compare changing state to reactant. So mark it in here. Natural log K is this. So natural log K will be T minus delta H plus delta. So this is enthalpy. Of activation. This is entropy of activation. And basically, delta S double dagger is defined as C double dagger minus A minus B. A plus B double. And we plug this into here. So K double dagger will be exponential of this. And the better way to look at this is to look at nature of that then K equals to T over H. This comes from K double dagger, small K double dagger, and then that is exponential this thing. So exponential minus delta H double dagger RT times exponential delta S double dagger over R. And actually, a better way to look at this is you have K over T, you move this T here. So the nature of rate constant over T equals to here RT minus delta H double dagger. So put specifically right times 1 over T plus you have this constant term here. So natural log KB divided by H from constant. And you have exponential take natural log delta S W R. And what this means is you can do a temperature dependent experiment to measure rate constant. The thing is always rate constant can be measured experimentally at different temperature. And you plot natural log over K over T. So you plot versus 1 over T. And actually, it will be linear to 1 over T. And slope is negative. So you go to higher 1 over T, means lower temperature. And this value will be smaller. So experimentally, it will be something like this. This experiment. And the slope would be and the intercept here will be interestingly, this constant contains the ratio between Boltzmann constant versus Planck constant, statistical mechanics or thermodynamics versus quantum mechanics. But those are fundamental constants. We know the value. So you can figure out entropy of activation and enthalpy of activation in this kind of experiment, temperature dependent experiment. And very often, this enthalpy is dominated by energy. So this enthalpy of activation tells us information about the activation energy over the system. And this is an entropic factor. Later on, we are going to, we will make use of these equations to understand many different factors controlling chemical reactions. But later, when we, in particular, when we talk about reactions in solvent, in solution phase, then how entropy factor, how the enthalpy factor. So this is enthalpy, this is energy factor. Entropy, entropic factor. How they control the reaction rate and how sometimes there's a competition between them. Okay. That's all I have for today. And it's a complicated subject, and I make my effort to try to simplify the reason. But you need to actually I encourage you to read the textbook. If we are really interested in this, please read Levitt, chapter 22 on this subject. Levitt has a more detailed discussion. Although I don't, it depends. It's not for everybody. It might not be easier to understand. And Bob Selby has a rough kind of hand-waving arguments on those. If you do not pay attention to detail, you could be confused. You could feel it's quite confusing for this part. But if your intuition fits with this physics, then you will find it actually straightforward to understand. Okay? I actually have a quiz problem. We don't have time. I'm going to give this paper to you, and we'll discuss this next week. We'll have a discussion on this next week. So try to practice. You don't need to turn in the paper next week, but I encourage you to practice. And if you have questions, you can ask the question next week. Those pictures will show up on next week's slides. I'm going to explain this.